So here's a quick outline of today's lecture. Today we are going to review this KW relations, which is this bridge between communication complexity and circuit complexity that we saw in the last lecture. And based on this connection, I want to uh, introduce a weakening of this relation. It's called universe relation. And with this in hand, so this conjecture is a very hard problem. So the first question to ask is how do we start making progress towards it. So we want some kind of weaker versions of this conjecture so that making progress is not too unimaginable. Versus, I mean, if you solve the conjecture, you know that you could settle P versus NC1, and this is considered to be a very hard long open problem. So we will see three weakenings based on this relation that we're going to introduce called universe relation. And two of them is something we already know how to make progress on. We know how to prove lower bounds, and the third one is sort of the frontier in this kind of research, and it's a hard problem. So let's just start with review of KW relations. So we said that this was instead of so the KRW conjectures about depth of Boolean functions. There's another alternative way to study depth of Boolean functions. This was through communication complexity and the communication complexity of a specific relation called KW relation. So given a Boolean function f, the KW relation associated with f, denoted by KW of f, is basically this two-party communication problem. There are two players, Alice and Bob. Alice gets x and f inverse of 1, Bob gets x and f inverse of 0, and the goal is to find an index I in n, so there are n bits of input in x and y, right, such that xi is different from yi. Okay, and the communication complexity of this relation is take any kind of deterministic protocol that solves this relation and look at the maximum number of bits communicated in that protocol, and that's the communication complexity of that protocol. And the communication complexity of the relation is the minimum communication complexity amongst all the protocols that solve this relation. Okay, so what Kashmir and Wigderson proved is that the communication complexity of this KWF relation is exactly equal to the depth complexity of the function f. Okay, so this is the KW relation associated with a function. So now I'm going to introduce something that generalizes this KW relation. So what are we going to do? So we are going to introduce something called the universal relation. But this is a sort of a promise problem. So remember in the KW relation associated with f, Alice and Bob were given two n-bit strings. So here also we are going to give them 0 1 to the n, and y is in 0 1 to the n. And this is a promise problem because we are going to promise them that x is guaranteed to be different from y. Okay, so we guarantee that whatever protocol they come up with, they only need to run on inputs where they're guaranteed that x is different from y. And the goal, as in like in the KW relation, is to find an index I in n such that x is different, xi is different from yi. Remember that in the KW relation associated with a specific function f, so this x was from f inverse of 1 and y is from f inverse of 0. And because of this reason, because f evaluates differently on x and y were guaranteed to be different, right? So only Alice gets only positive and one inputs of f, and Bob gets only 0 inputs of f. So there's a natural partition of the Boolean hypercube, and one player gets only strings from the first partition, and the other player only gets things from the second partition. But here in the universal relation, we are literally taking this function out of the picture. So we want to say this is the relation associated with any kind of Boolean function. So once you take this function out of the picture, once you take this guarantee that there is some Boolean function where x evaluates to 1 and y evaluates to 0, it's not necessary that x is different from y, right? So the only reason in the KW relation of f that x was there was an index such like I where xi is different from yi, or in turn x is different from y, is because x and y are guaranteed to be different, because x evaluated to 1 on f and y evaluated to 0 on f. Yeah. So we take this function out of the picture, but then we need to like make sense of this finding this index business. So we bring in this promise, and this promise says that the players need to design a protocol that works only when this guarantee is true, like x is different from y. So we'll denote, okay, so again, what are the parameters? So we'll denote this by u, and we will use a subscript n to denote the number of bits in the inputs of Alice and Bob. So if un is the promise problem, where Alice gets an n bit string x and Bob gets an n bit string y, where x is guaranteed to be different from y. And the communication complexity of the universal relation is again like communication complexity of like the best protocol that solves this relation. So just to denote, so notation, un is universal relation on n bits. Okay. So here is an interesting fact about universal relation. As I was telling you earlier, we wanted to sort of generalize and come up with a notion that works with any function, KW relation of any function. So here is the thing. Suppose you have a protocol that solves universal relation. You can also use that to solve the Kashmir-Wigderson relation of any function. So in turn, so here is a fact. It's easy to check. The communication complexity of the universal relation is at most is an upper bound on communication complexity of Kashmir-Wigderson relation for any function f, for any f on 0 1 to the n to 0 1. Okay. Why is that true? So what we're going to argue is that like take any protocol pi that solves this universal relation, then given an instance of a KW relation, you can use that protocol pi to solve the KW relation associated with f. So here is what we're going to prove. This is simple proof. So pi solves universal relation on n. So what does that mean? So whenever Alice and Bob are given strings which are guaranteed to be different, it finds an index I where xi is different from yi. So if pi is run on x comma y, then it produces an index in n such that xi is different from yi as long as x is not equal to y. So now if you think about the KW relation of f, all the inputs Alice and Bob get satisfy this promise, right? So Alice gets x in f inverse of 1 and Bob gets y in f inverse of 0. So they naturally satisfy this promise that it implies that x is not equal to y. So whenever like whatever input do you have for a KW relation of f, you can take that input and run the protocol for universal relation and you will get the output, which is what you want in the KW relation associated with f, right? So this is just a simple fact and a simple proof. Yeah. So are there any questions at this point? So this would be a good point to pause and ask questions if you have any. Okay. If not, yeah, let me move on. So now, yeah. So this is sort of a generalization, and I call it a weakening for a very good reason. We'll see that in the later lectures. We'll actually prove lower bounds for universal relation and universal relation composed with other things. But why did we introduce this relation? So we wanted to, so saying the KRW conjecture is a very, I mean, because of the implications of the KRW conjecture, it's a very hard problem. So we want some kind of weak versions of the KRW conjecture, which intuitively make sense and on which we can hopefully make progress. So what was the KRW conjecture in terms of communication complexity? Just restated in terms of communication complexity. So given two functions f and g, again as ever, whenever we consider this f and g, they're assumed to be non-constant functions, otherwise the conjecture is not true. It said that if you look at the communication complexity of the Kashmir-Wigderson relation associated with f composed with g, that's approximately equal to the communication complexity of the Kashmir-Wigderson relation associated with f, and plus the communication complexity of the Kashmir-Wigderson relation associated with g. Okay, so now to make progress, what we are going to do is like we want to so here we are talking about composition of two functions. Now we would like to talk about composition of universal relation with the function or universal relation, etc. So functions are hard. I claimed without proof that universal relations are easy, and so we want to understand compositions of functions by building intuition towards compositions of universal relations. And then yeah, so but before I do that, I need to define composition of universal relation with a function. So what are we trying to do? So we want to define weakenings of this conjecture. So we'll first see how to compose universal relation with a function. So this is composition of universal relation with a function. So for this, let's go back to the definition of composition of f composed g. So recall that f composed g, we wanted to like, so f is an m-bit function, g is an n-bit function. We wanted to think of like it as a function on mn bits, and the way we viewed this input to f composed g, so f composed g is a function on m cross n bits to 1 bit. This is from lecture 1. So you want to think of input to f composed g as a Boolean matrix, so which has m rows. So there are rows 1 to m, and there are n columns 1 to n. And how did we get f composed g? So we first so g is an n bit function. So this is n bit, and f is on m bits. So you first apply g to the individual rows of this matrix. So each row is exactly n bit, and that's the input size of g. It matches up. So by applying this, so let me call this x, and by applying this, we would get like m new bits. I don't know. So call this a. So just apply g on this individual rows, and then you will get a column vector of exactly m bits, right? And this is an input to f. So now you apply f on this, and then you get a 0, 1 value. Okay, so this was how the composition of f and g were defined. And now what was the, so let's try to recall the Kashmir-Wigderson relation associated with f composed g. So we do this. So what was Kashmir-Wigderson relation associated with f composed g? So Alice gets a 1 input of this f composed g, and Bob gets a 0 input of f composed g. So the way we view it again is like as a matrix and a vector pair. So Alice gets a matrix x, m rows, n columns as before, and then she applies g on this matrix to get a column vector a, which is 0, 1, whatever. But the guarantees, so here there is a promise involved in this KW relation, right? It's not like any input of f composed g. So Alice gets a 1 input of f composed g. What does that mean? So if Alice applies f on this column vector a, what should she get? She should get 1, right? And now similarly Bob gets so let me just erase this and make some space. So if you apply this on this, you get 1, and Bob gets similarly like a vector b. So he gets an input matrix y, he applies g on this input matrix and gets m bits, which we call b, I don't know. And then we know that if you apply f on this, we should get 0, right? So this was the Kashmir-Wigderson relationship, so a relation associated with f composed with g. Okay, so this also had a, like, so in terms of uh, when you think about f composed g, there was also the circuit definition. um, but now, from now on, we are going to look at this communication definitions. Whenever you want to study depth of something, we'll study the communication complexity of this relation. So this is a setup for f composed g. So now we want to study this weakening, to like where we want to replace a function with a universal relation. So let me define the Kashmir-Wigderson relationship associated with the universal relation on m bits composed with g. So remember that f was a m bit function, and we sort of intuitively saw that universal relation on m bit sort of generalizes the Kashmir-Wigderson relation of any Boolean function f on m bits, right? So we want to replace f with the universal relation on m bits. So how do we do this? So if you remember the plain vanilla universal relation, it was a promise problem, and there's no like function or there's no Boolean function associated with the universal relation. So we cannot think of like a circuit definition and then like define an equivalent communication version based on that. So we have to like somehow make sense of this problem by coming up with a good definition. So here is a good definition that works. So what are we going to do? So in the universal, in the so when we moved from the Kashmir-Wigderson relation of f to the universal relation on m bits, what did we do? So remember, in this case, Alice and Bob were given inputs where x was from f inverse of 1 and y was from f inverse of 0, and we replace it with just any x and y, as but with an extra promise that x is not equal to y, right? So what is the input of f in the Kashmir-Wigderson relation associated with f composed g? So in this setup, so the input to f on Alice's side is this column vector A, right? And the input to Bob on f on Bob's side is this column vector B. So we want to take out f from this picture and replace it with the universal relation, or rather by a promise. So this is what we're going to do. So this is a promise problem where Alice and Bob get the following kind of inputs. So Alice again gets an m by n matrix X. X has, as usual, m rows and n columns. Yeah, and now what so we haven't replaced G, so she has access to G. There's some G that both Alice and Bob know, so she applies G on individual rows of this matrix, right? G is again an n bit function, so she can do that, and then she gets this auxiliary input A, this column vector A. This is without communication. Okay, so that's that. And Bob gets another matrix Y such that this has m columns. Again, it's an m by n matrix, and there are there are m rows and n columns. And Bob does the same thing. He applies G on this matrix Y and gets a column vector B. But recall that there is no function in the picture anymore. We are working with universal relation on m bits, so we are supposed to like come up with some kind of promise problem, right? So the promise is going to be that promise is sort of indirect. It says that, so I'll denote applying, so I'll denote this column vector as G applied on this matrix X. So what does that mean? So we apply G individually on each of the rows, and then we get an m bit input. So A is an m bit string and B is G applied on the matrix Y. So this is just some notation that we're going to use. So X is a matrix and G applied on X means G applied individually on the rows. So the promise problem is going to be that Alice and Bob get x and y such that this a vector that they get, which is g of x, is guaranteed to be different from the b vector that Bob gets by applying g on y. Yeah, so hopefully this makes sense. So earlier they were promised that if you apply f on a you get 1, and if you apply f on b you get 0, and this guaranteed that a and b were different inputs. And in the universe relation there's no function in the picture, so all you care about is that they're given two m-bit strings which are different. So this is the promise they're going to be given. But since they're given this huge input x and y, the promise is on the input slightly indirectly. So if you apply g on x, you get a vector a, and you apply g on y, you get a vector b, and they're guaranteed to be promised to be different. So now you can see that this is actually a generalization of KW f compose G for any f. So what do I mean by that? So this was a definition. So are there any questions about this definition? So just a subtlety here is that earlier these definitions had some kind of meaning from this block composition of functions. So here we had to like universal relation doesn't correspond to any specific Boolean function. So we had to come up with a definition that sort of makes sense. Yeah. That sort of generalizes all kind of KW relations. So here is the earlier kind of simple fact for universal relation generalized for this specific composition. So it says that communication complexity of universal relation on m bit composed with G is an upper bound for KW f compose G for any f on m bits. And the proof is pretty much the same. You take any protocol that solves this problem. So let's say you have a protocol pi that solves this problem, and then you're given inputs which are which are according to this problem. So Alice is given an x such that f applied on a gives 1, and Bob is given a y such that f applied on b gives 0. Then I say that this is a pair of inputs that is legal for KWUM compose G. So what do I mean by that? So any input here satisfies this promise, right? So that is easy to see. So any xy inputs that come from Kashmir-Wigderson relation of a specific function composed with another specific function satisfy this promise in this new definition. Why? Because f of a is 1 and f of b is 0, a is different from b. This is simple reason, right? So this indeed shows that, okay, so this universal relation indeed generalizes this composition. So if you replace a function with the universal relation in this specific composition, it indeed generalizes in the sense that any protocol solves that this generalized problem solves also this specific problem of f composed with G. Okay, so now the other question is like, why stop there? Maybe so we started with KW of f compose G, and then we move to KW of universal relation composed with G. Maybe we can replace G with universal relation at this point. So how do we do that? So let me just copy this definition again. Yeah, so just to have this as a reference. So here, so what are we trying to do? We are trying to come up with a definition for Kashmir-Wigderson relation of f composed with a universal relation. So f is an m-bit function and g was an n-bit function. We want to replace it with universal relation on n bits. So this is slightly trickier than the other definition. So let's try to work towards this definition, and you'll see why. So we have, yeah. Uh-huh. Mm-hmm. Yeah. uh no. So yeah, so the first part, okay, so that's an interesting question, we'll come to that. Yeah. So your concern is that, like, when, if so if the rows should correspond to universal relation, and then if we solve universal relation on these rows of the matrix, we'll get a bunch of indices, and then what do we do with that? So the, yeah, that's not the way to go about it. So the way to go about it is slightly different. So we want to, like, yeah, so just as I was saying, like, we have f in picture and we don't have any g, but recall that op- f is applied on a. And how did we get a? A was obtained by applying g. And as Sam was just saying, like, you cannot apply universal relation on an input string, right? Because universal relation doesn't correspond to any function at the, like, and even it doesn't even give an index. It gives an index if like, if you take a row of Alice, which is, let's say, xi, and if you look at the corresponding row of Bob, then if they are guaranteed to be different, you sort of get that, okay, there's some in, like, the answer of the universal relation is some index where they differ. But that's not a boolean value, and that's also not dependent on Alice's input alone. So there's no, like, meaningful way to get a vector out of x using universal relation, and there's no meaningful way of getting a b out of y using universal relation. So this is a problem. But okay, so what are we going to do? So we wanted to, like, okay, so this is something from the first lecture. So whenever I introduce, I think, yeah, when, or maybe the second lecture, when I introduce this KWF compose G, I told you that there's this naive protocol. Oh, uh, so I did say this for the circuit definition of this thing. So when we introduce F compose G, I said there's a naive circuit that computes F compose G, and the conjecture says that that circuit is optimal in terms of depth. But you could, like, take that circuit, and then we can say an equivalent thing about the a naive protocol solving the Kashmir-Wigderson relation associated with F compose G. So just to refresh your memory, so this is that protocol. So okay, so that's where we're going to start. So remember, the goal is to define this, and we ran into this hurdle that to, like, make sense of a and b, we needed a g, and we currently don't have any good definitions. So what are we going to do? We are going to see a naive protocol that solves F compose G. But it's not so naive either. It uses the optimal protocol for, so let's call this, so let's denote by pi f the optimal protocol that solves KW of f, and pi g is defined similarly. Yeah. So we're going to build a protocol that solves this Kashmir-Wigderson relation associated with F compose G using protocols pi f and pi g. So this is sort of naive in the sense that it's not doing anything crazy for F compose G, but it is using, like, two building blocks, a protocol for KW of f and protocol for KW of G. Oh, by the way, just to remind you, what's the goal in KW of f of G? it's it's to find an index I comma j. So I is a row, I indices, like, indices into a row, and j is a column, such that Xij, the input to Alice, is different from input to Bob. So you want to find an entry in this matrix, let's say this entry, and maybe this is the corresponding entry, so that whatever is Alice's input, it's different from Bob's input. So that's the goal here. It's just from the definition of a Kashmir-Wigderson relation. So whatever is, so the input to F compose G is X, and input to F compose G on Bob's side is Y. And in the Kashmir-Wigderson relation, so the final goal is to find, an index where X and Y differ, right? So this was the goal, just to highlight. So you want to design a protocol where you given this X and given this Y, you want to come up with the index ij where they differ. So here is the way to use pi-f and pi-g to solve this problem. So what do you do? So the first, it has two stages. Okay, so the first stage, so as before, like, because we have F and G, Alice can compute A without any communication and Bob can compute B without any communication. So we really think of their inputs as X comma A and Y comma B. Okay, and this is without communication. So the first stage is to run pi f on A comma B. So what would that do? So first of all, we have to make sure that A comma B is a valid input to pi f. So pi f solved the Kashmir-Wigderson relation of f. So whenever A is an one input of f and B is a zero input of f, pi f is guaranteed to return. So what would it do? It returns I such that AI is not equal to bi, right? So we can take this A and take this B, and it satisfies the guarantee given in the Kashmir-Wigderson relation of f. So we just run pi f on A comma B, we get an index where AI is different from bi. Are we done? No, we want, this is not enough, we want to find an index in the into the matrix where they are different. So we have so far gotten an index where they're different, but in this augmented input that they are imagining. But this is where pi g comes into play. So what does it mean to say that AI is different from bi? So under our notation, so recall that g of xi, so g applied on ith row is AI, right? So g of xi is AI. Let's say g of xi is, just to make things harder, g of x, this AI is 0. So I don't know if AI equal to not equal to bi, is it 0 1 or 1 0, but just to make my life hard, so I'm gonna put 0 here. And then what is bi? That is g applied on the corresponding row but on Bob's side, so it's g of yi, so that is bi is 1. So without loss of generality, I'm assuming that one is 0 and the other is 1, and equivalently you can do the other case. That's easier, in fact. So now to run the second stage, we take pi g. In pi g, Alice is supposed to get a 1 input of g, and Bob is supposed to get a 0 input of g, and they're supposedly working on n bit strings. So what is the length of xi? It's an n bit string, right? A specific row of this matrix has exactly n bits because it's the number of columns. So this is an n bit string. Oops, my n's are not okay. So is this. So xi and yi are inputs to KWG in terms of length, but in this specific scenario that I'm considering, g of xi is 1, and that's what Alice has. Sorry, it's 0, that's what Alice has, and g of yi is 1, and that's what Bob has. But in the KW relation for g, Alice is supposed to get a 1 input, but here we have a 0 input. So what do we do? So if this is the case, Alice knows that she is the 0 player and Bob knows that he's the 1 player, and they have a protocol where Alice is supposed to be the 1 player. So what do we do? So they take this protocol, and whenever Alice is supposed to speak, Bob will speak, and whenever Bob is supposed to speak, Alice will speak. And this they can decide by looking at the value of AI and bi individually. They don't need communication for this. So what are they going to run? They're going to run pi g on this xi and yi. Okay, so maybe what they have to do is like switch the roles of Alice and Bob in the description of pi g. If pi g says Alice send the first bit, so here Bob will send the first bit. Okay, that's a um yeah, so you're saying that like, yeah, KW of f complement is the same thing as like the communication complexity of f complement is same thing as f. Yeah, so that also you can see from the circuit version. So communication complexity of KW of f is just the depth complexity of f. So if you have a De Morgan formula computing f, you can just apply a negation on top and push it all the way down without changing the depth. So the optimal depth of computing f and f complement are the same. Uh-huh. Yeah, it would, in fact, that's actually a good point. So when we like I guess you were not there, for in the last lecture we saw that how the Kashmir distance. So if you have a circuit for f, then you can get a protocol for KWFF, and in that protocol construction that we described, if you push a negation through, every AND gate will become an OR gate and OR gate will become an AND gate. So that's just in that protocol, it's just switching Alice's role to Bob and Bob's role to Alice. Yeah, good points. Yeah, so it's not difficult. So they just like look at AI and BI based on whether it's 0 1 or 1 0. They either run pi g as it is, or they run with Alice and Bob flipped. So what do we get at running pi g? So by running pi g we get an index j. So this is an index in 1 to n, such that this this string xi is different from string yi at j. So if you write it out, that's saying xij is not equal to yij, just by the guarantee of pi g, right? So by running these two stages, we have indeed solved the Kashmir-Wigderson relation associated with f compose g. Yeah. So so what did we prove here? We just proved that, okay, so if you have the best protocol, like if you have a protocol for KW of f and a protocol for KW of g, then you can get a protocol that solves KW of f compose g. And if you notice, what is the communication complexity of this new protocol? So let me call that pi f compose g. So the communication complexity of this uh, pi f compose g was communication complexity. So it was the communication complexity of the first stage, which is communication complexity of pi f, which is equal to communication complexity of KW of f, because we started with that best protocol for KW of f plus communication complexity of pi g. This is KW of g. Oops. Communication complexity of KW of g. So this just says that, so this is a protocol that solves KW of f composed with g. So the optimal protocol for KW of g cannot have a higher cost than this. So this says that the communication complexity of the KW of f composed g is at most the communication complexity of KW of f plus communication complexity of KW of g. So this was the EC direction of Kashmir-Wigderson conjecture, right? The conjecture says that it's approximately equal, so it should be at least this much modulo some uh, multiples and constants, but and it should also be at most this much. So this is the at most part, and this is, so this was the proof for that. We saw this equivalently using circuits, where we proved that the depth of f composed g is at most depth of f plus depth of g. Yeah. So and the conjecture is basically like, okay, so the various attempts at proving this conjecture has been trying to prove that this protocol is optimal, is indeed optimal if you're trying to solve F compose KW F compose G. So what do I mean by that? So this sort of, so we solve the problem in two stages. So this staging is sort of necessary. So they have to first communicate some bits to solve KW of F, and then they need to use that information to solve KW of G in the second stage. But the conjecture doesn't say something like that. It just, because addition is like, I can write uh, a plus b as b plus a as well. I can as well write it as cc of kw of g plus cc of kw of f. So conjecture doesn't distinguish, like this, the exact statement doesn't distinguish between these kind of stages. But the main intuition behind the conjecture is that the hope is that this is the optimal structure of any protocol that solves F compose G. So if to solve the problem associated with F compose G, you have to first solve F and then solve G. We'll later on in this week we'll see some justification. Okay, I mean not mathematical justification, then we would prove the conjecture, but intuitive justifications for why this ought to be the case. Okay, but again, these are just guidelines, and maybe if you're trying to disprove the conjecture, then you should really try to understand why this intuition doesn't make sense. So here we are. So what did we do? We wanted to somehow define KW of F compose G, but sorry, KW of F compose universal relation, and we saw that there's no easy way to do this. So what we're going to do is, like, we take this philosophy for granted that this naive protocol is also the optimal protocol, and then we're going to define the KW of F compose G based on this. So let me copy this naive protocol over, and then we will see the definition of oops, okay, I guess I need to be a bit careful here. So we are going to sorry, we are, so our goal, define the Kashmir-Wigderson relationship associated with F composed with universal relation, so that this kind of naive protocol works. And then we can say that, okay, this is also the optimal. Okay, so just remember this was the naive protocol for F composed G. So here is what we're going to do. So I claim that, okay, so I'm going to define this thing. So the definition is going to be, so I'll write down the definition. I'll tell you why it makes sense in terms of this naive protocol. So Alice and Bob in this, so this is the definition of KW F composed universal relation. So Alice gets an matrix X, which is m by n. So there are m columns and n rows. And Bob gets a matrix Y, but they have, like, again, the dimensions are the same. Okay, so we saw that, like, earlier we could get this vectors A and B by applying G on the matrix, but there's no G in picture anymore. Universal relation doesn't give you a Boolean evaluation. It doesn't correspond to any kind of Boolean functions. So what we're going to do is, here we're going to expand their inputs by giving some extra vector, which we call A. So it's only loosely related to this X via a promise, and we'll see what that promise is. Okay, so there are going to be two promises here. So you can think of, for now, you can think of this as independent inputs A and B. So they get an m by n matrix and 1 by m column vector. So they get two inputs, but there are some promises that are given to the players. So we will build these promises so that this naive protocol can solve the associated Kashmir-Wigderson relation. Okay, so what is the first promise going to be? So we want to, so in the first stage for the naive protocol, we want to say that you can apply the Kashmir-Wigderson, like you can apply a protocol pi f that solves KW of f on a comma b. So the promise one, so let me write this with red or blue. So promise one, so here it is a promise problem. So this is a promise problem. Like in the universal relation, right? I mean, in the universal relation, the simplest universal relation that we defined, Alice was given an x and Bob was given a y, where x was different from y. So that was a promise problem. This is equivalent. This is another promise problem. So there are two promises. The first promise is that the inputs a and b are such that f of a is 1 and f of b is 0. So indeed, a and b are inputs to the Kashmir-Wigderson relation of f, right? So if you're given this promise, so the players are given this a, which is like not related to x by some function or anything. It's not an evaluation of x on some g, but it's like an independent input now, and b is another independent input. But the constraint is that they're guaranteed that f of a is 1 and f of b is 0. So now they can run I claim that they can run the first stage of the protocol just because of this promise. So remember this naive protocol, and this was for KW of f composed G, and we are trying to like make sure that we come up with a definition for f composed UN, so that this naive protocol can solve this Kashmir-Wigderson relation as well. So in the first stage of the naive protocol, what are we going to do? We are going to run pi f on a comma b. So what would that give? So if you run pi f on a comma b, it would give an index I such that ai is not equal to pi. And why can we run pi f on a comma b? It's simply because of the promise. It's okay. This was f. Sorry about that. I've run out of space there. Because of this promise, we are given this promise one. So because of this promise, we know that f of a is 1 and f of b is 0. So we can run this. So at the end of it, we get an index where these column vectors differ. But now, so what would be the second stage for the naive protocol for KWFF composed to UN? So in the first stage, you run the best protocol for KWFF, and in the second stage, you run the best protocol for the universal relation. There's no G here, so we cannot talk about KW of G, so there's no pi G in picture. So in the second stage, we want to run the best protocol for universal relation on n bits. But okay, so here, so what are possible inputs that we can run on? So maybe like, so we have narrowed down on this specific row of x and y. So this is xi and this is yi. So maybe we can run universal relation on these rows. So the universal relation on n bits expects n bits of inputs for Alice and n bits of input for Bob. But so the input sizes match because we are looking at n columns in this matrix. But there's this other problem, right? If you want to run the universal relation on n bits on a string xi and yi, we need the guarantee that xi ought to be different from yi. Earlier, in the other case, this was given because this ai was g of xi and bi was g of yi. So we were guaranteed that xi is different from yi because g evaluated differently on these inputs. But there's no g in picture, so there's no real guarantee that xi is indeed different from yi. I mean, if you think about it, so far there is no relation between the matrix x and the input a and the matrix y and the input b. So why should you get anything from like an index where ai is different from bi? So here's where we are going to bring in the second promise. The second promise is going to say that whenever these inputs ai and bi are different, we would guarantee that the corresponding rows are different. So this is promise 2. So promise 2 is a little more elaborate. It says that for all indices I in M, if ai is not equal to bi, this implies that xi, the corresponding row of Alice, It's different from corresponding row of Bob. So this is promise 2. So remember that uh, this is what G guaranteed. If there was a G that gave AI and there was the same G gave BI, it would indeed imply that Xi is different from YI, but we don't have a G, so we replace it with a promise. So this is the mantra of universal relation. You don't have a function, and functions gave some kind of guarantee on the inputs. You replace that guarantee with a promise that, okay, the players need to solve the problem only on the inputs that satisfy this promise. So so this is a bit of an unnatural definition, but once you have seen all this, maybe this is natural to you, and you can see that now we can follow this naive protocol, this strategy of naive protocol, to solve KW of F composed UN. So what do you do? So this is the naive protocol for KW of F composed UN based on, okay, so as before, pi f is the optimal protocol for KW of F, and let me denote it by pi n, the optimal protocol for universal relation on n bits. Okay, so how do we do this? So Alice and Bob, just to let me redraw this. Alice gets an input X, and now there's an additional input A. This is not generated automatically or defined equivalently. There's an additional input A. So X is just m rows and n columns, and this has m bits, 1 up to m. And Bob gets Y, same dimensions. So X and Y are the same dimensions, A and B are the same dimensions. And they get these two promises. Promise 1, f of A is 1 and f of B is 0. Promise 2, whenever AI and BI differ, so for all I in M, if the bits AI and BI are different, if AI is not equal to BI, that implies that the corresponding row of XI and YI are different. Okay, so now let's run the naive protocol. So the naive protocol is going to be first stage, again the same two stages from our philosophy. Run pi f on a comma b. This gives you an index I such that AI is different from BI. And now I claim that because of promise true, like in because of promise true, promise 2, we know that Xi is, because AI is different from BI, because of promise 2, we can run pi n on Xi yi. So remember that in the universal relation on n bits, the protocol is supposed to get, Alice is supposed to get an n bit input Xi, and Bob is supposed to get an n bit input Yi, such that Xi is different from Yi, and because of promise 2 and the fact that AI is different from, and this fact, we know that Xi is different from Yi. So we can run this protocol, and then we can find an index j in n such that Xij is not equal to Yij. So now based on this protocol, I'm going to define the goal of Kashmir-Wigderson relation associated with F composed UN, and it's the same as the goal in F, the Kashmir-Wigderson relation associated with F and F composed G. It is to find a bit of difference in the inputs X and Y. So you want to find an Ij such that Xij is different from Yij. So this is maybe 0 and this is 1. So they can't, they're not good with just finding a difference in a comma b. They can find, but that's not the answer. So the answer we are looking for is an index in these matrices, not these column vectors, but in these matrices where Xij is different from Yij. So this is going to be the definition. So just to recap, so this is our definition, and this is this is the motivation for this definition, that we wanted to follow this philosophy that okay, whenever you see a function in universal relation, we replace with a promise, and we wanted to generalize so that this naive protocol based on the optimal protocols for F and G philosophy worked even in this definition. So based on the naive protocol for F and naive protocol for universal relation, we can build this, sorry, optimal protocol for those, we can build a naive protocol for this in the same spirit. And what we want to prove that this kind of two-stage approach is optimal. Okay. Oh, but then you would be so, so you're suggesting like why don't we apply F on Xi's and get A? So the partition is described by some function, right? Yeah. So but then we are back to KW of F compose G for some G, right? So yeah, so if you wanted to like so what you're suggesting, if I understand correctly, is that like why do so if it, oh so then you're like looking at the composition of F with itself. So you're saying that so you're saying keep promise one. What are you going to do with promise one? So we wanted A comma B to be an instance of Kashmir-Wigderson relation of F. Yeah, yeah, yeah. So, so the sort of thing that you described is like the other thing, right? I mean, it's the G composed universal relation. If you didn't have P1, then yeah, yeah. Are there any other questions about this definition? This is a bit unintuitive, but I hope at this point this is intuitive to you. This definition. Okay. Okay. If there are no more questions, so let me just yeah. Why did we introduce this all? Oh, I want to tell you one more weakening, and that's going to be the theme of this week, like composing universal relation with the universal relation. So for what have we done? We had F compose G, so we either replaced F with a universal relation of comparable size or G with a universal relation of comparable size. So like why stop there? Let's go all out, and then we're going to replace F and G with universal relations. So let's take this as a starting point. So we what we want to do is like we want to define, oops, wrong ink color. So goal, come up with the same definition of Kashmir-Wigderson relation associated with an m-bit universal relation composed with an n-bit universal relation. Okay. So as a starting point, we'll start with the setting of the last slide, which is F composed with a universal relation. So what are we going to do? Like the players get two inputs. This is going to be simple once you have seen the other definition. That's why I'm introducing it in this order. So they're getting two inputs, X and A. Okay, so maybe this is the last lecture when I'm going to mention the dimensions of X and A. X is an m by n matrix and A is a m-bit vector. So if you're ever confused about the dimensions, please ask me. And in the KW of F composed universal relation, there was no particular relation between X and A and Y and B except for this promise. So let me write down those two promises. So this is 1 to M, this is phi. So there are two promises, so we'll have to modify one of them. So one promise was that f of A is 1 and f of B is 0. And the other promise was that okay, whenever you solved the Kashmir-Wigderson relation on this vector and you found an index where they differ, then you wanted to run the second stage on the corresponding rows, and you wanted this guarantee that whenever AI is different from BI, you wanted the corresponding rows to be different. So this is this promise that for all I in M, xi is different from yi. So these matrices x and y are related to A and B through this promise 2. Yeah, otherwise they're fairly independent. I can give any m bit vector such that f of A is 1, and any m bit vector b such that f of B is 1. And once I have that, I can sort of give all kind of Boolean matrices x and y as input to Alice and Bob, but I have to satisfy promise 2. But now we are trying to, so what we had, okay, so what we had, let me write this in red. So what we had was f composed with un. So that's why we had this p1. So we want to replace now f with a universal relation. So if you remember, what was the trick? To take f out of picture, we wanted, so what was the purpose f was serving? F guaranteed that A was different from B. So f implied that existence of f implied that A is not equal to B, right? So we want to take f out of picture. So what do? We replace it with this promise. So this is a complete promise problem. There's no f and g in picture. So the second promise remains as it is because that was already a universal relation. The first promise is that A, oops, okay, guess I have to erase this again. So A is different from B. The vector, so they're given like completely independent inputs, xa and yb, with these promises. The first promise is that A is not equal to B, and the second promise is that whenever, oh, so I did not write this promise 2 completely, sorry for that. So this should have been, if AI is not equal to BI, then XI is not equal to YI. Okay, sorry about that. So these are the, so this is the setup of KW of UM composed with UN. So these are the valid inputs. So this is the, so the inputs should satisfy promise 1 and promise 2. So this is also a promise problem. And what is the goal? And the goal is, can someone make a guess? What should they find? I mean, we wanted to generalize Kashmir-Wigderson relations of F compose G, right? In F compose G, they were supposed to find index I comma j, some entry in this matrix, corresponding entries in this matrix where xi was different from yi. So that's the goal here as well. Some ij, so I is a row and j is a column. So this is an entry of the matrix such that xij is not equal to yij. So find ij, such an ij with minimal amount of communication. And now again, so one thing to check is like whenever we build these definitions, does our naive equal to optimal philosophy from this composing the optimal protocols work? So this is the definition of Kashmir-Wigderson relation associated with universal relation on m bits composed with universal relation on n bits. Are there any questions about this definition? So it was just fairly straightforward to define it once we had this definition. Okay. And we wanted to make sure that this kind of first stage, second stage strategy worked. So why should that work again? So like, yeah, this is fairly straightforward. So you take a protocol, let me call it pi m. So that's the optimal for UN, universal relation on m bits, and pi n is the optimal for universal relation on n bits. So what do? So you first, so I'm running out of space here, so just try to squeeze it in here. So if you people cannot see, let me know. I don't know how big this appears on your screen. So you first, so you're given these inputs with this x comma a and y comma b which satisfy these promises. So you first run pi m on a comma b. And why can you do that? Because a is m bits, b is m bits, and a is guaranteed to be different from b because of promise 1. Because of this, we can run this. So you run pi m on a comma b, we get an index such I such that this gives I such that ai is not equal to bi. And now the moment we get this index ai is different from bi, promise 2 kicks in, right? So now promise 2 kicks in, and promise 2 tells us, oops. So the promise 2 tells us that whenever ai is different from bi, xi is different from yi. And that's the only promise that we need to run by the universal relation on n bits on xi and yi. So what do? Very straightforward. Run pi n on xi comma yi. So this should give you a j such that, okay, I'll make some space here. Xij is not equal to yij. So this is like, again, we had this strategy. We first zoomed in on a row where the players are supposed to be different, and then we went into that row and found an index where they differ. So this solves the problem, and this, so with this definition, we can say that like we can run this two-stage protocol. Yeah. So this sort of completes these three definitions. And why did we invent all these definitions? Because we wanted to study this conjecture, right? So which was hard. So the original KRW conjecture said that communication complexity of the Kashmir-Wigderson relation of F composed G is approximately equal to this first stage plus the second stage. So this is what we want to prove. So weakening 1 is when we replace F with a universal relation. So we want to say that this thing, sorry, get the picture. So the universal relation composed with a function, oops, okay, so this is the universal relation on m bits. So remember that f is an m bit function and g is n bits, composed with g should be approximately equal to the communication complexity. So remember that universal relation itself is a relation. There's no Kashmir-Wigderson relation associated with universal relation. So this is just communication complexity of the universal relation on m bits plus the communication complexity of the Kashmir-Wigderson relation associated with G. So this is the sort of equivalent conjecture that we get by replacing universal relation with a function. And the other things, right? Let me write this anyway. This is kind of boring. What would it do? It keeps f but replaces g with a un. And what should this be? The communication complexity of the Kashmir-Wigderson relation with f plus communication complexity of the universal relation. And the third one, well, that is, okay, so I should not have called this the Kashmir-Wigderson relation associated with the universal relation, because you can say that only if that makes sense only if you have at least one function in picture. So in this definition, we completely got rid of functions, and then there's no Kashmir-Wigderson relation. It's just this universal relation that generalizes all kind of Kashmir-Wigderson relations, right? So this is just denoted by composed to un. So this is, sorry for this mistake. So this says that, okay, so now you have gotten rid of all the functions from the picture. So this should be approximately the communication complexity of the inverse relation on m bits and the communication complexity of the inverse relation on n bits. Okay, so yeah, so here is something that we'll see in tomorrow's lecture, that the communication complexity of universal relation is super nice to analyze. So you can prove that okay, maybe not call it fact lemma. The communication complexity of universal relation on m bits is approximately m. So we know it precisely. It's like at least m plus 2. So this is like m plus 2, but I think it's at most m plus 3. So I don't exactly remember, but it's like m plus a constant. But remember that this is approximately equal to m. So this is like the sort of the hardest problem on m bits. So if you remember from the early lectures, any communication problem where one player gets an m bit string can be solved with m bits, right? I mean, Alice can send her entire input to Bob, and then Bob can solve it. And this says that roughly you need this much. So this is a hard problem. So this says that, okay, so this should be m plus this thing, so on and so forth. This should be approximately. So if you take the weakening number 3 and this fact, it says that this is approximately. So this thing is approximately equal to m plus n. And yeah, so the easiest of all these three is like this, where you don't have any functions in picture because of the proof techniques that we are going to use, and then we'll see that it is indeed close to m plus n. We can prove the KRW conjecture in this very weak special case, and we know how to get really good lower bounds in weakening number 2 also, but weakening number 1 is an entirely different beast. We don't have any non-trivial lower bounds here, so this is sort of like the odd person out. So this is like sort of the frontier in terms of techniques we know. There are like very few uh, no good choice of G. Like there for some like G's which are like tiny in terms of depth complexity, yes, you can get a lower bound. Yeah. Uh, yeah, also some other G's which I don't want to define right now, but yeah, we'll see. Like this is like, yeah, so that's going to be the last week of this course, so it's fairly advanced out there. But I just wanted to say that, like, because of this philosophy that you run the first stage and the second stage, it matters where this universal relation appears. So if we have universal relation in the first stage and the function in the second stage, it's super hard, and we are looking for techniques in there. So just to quickly recap, we wanted to like study this conjecture, but because this conjecture is super hard, we wanted some kind of weak definitions, um, where we can like use kind of intuition from this naive is equal to optimal philosophy and then prove lower bounds. Okay, so far I didn't convince you why this is a weakening. So one reason it is a weakening is that, like, if you prove any of these weakenings, you don't prove the original conjecture. Also, you don't get any of the associated lower bounds. So you don't get P not equal to NC1 from any of these three versions. Okay. Uh, so it doesn't imply the big breakthrough result. So maybe we are avoiding some barriers involved in proving that breakthroughs that we don't know yet. I mean, so one of the appeals of KRW conjecture approach for P not equal to NC1 is that all the kind of mathematical barriers that we know that rule out certain kinds of proofs do not rule out this strategy. But maybe there are, like, I don't know how to interpret that. Maybe that is good news or bad news. The bad news could be that maybe there's some kind of very specific kind of mathematical barrier that applies to KRW conjecture. So that's an interesting research direction as well. Or uh, there isn't one. So depends on which camp do you belong. And then the thing is that uh, if you believe that there are indeed barriers to proving the original conjecture, hopefully those barriers don't apply to these weakenings. And we know that for weakening 2 and weakening 3, we can actually indeed prove the conjecture. And the reason that they don't apply is that we don't get P not equal to NC1. So these mathematical barriers are from complexity theory, and if you are not getting a result in complexity theory, hopefully they don't apply.